Welcome, everyone. Come on in and get settled. If you are preparing to tackle those notoriously tricky Cambridge graph problems specifically for syllabus 0580, then consider this explainer your absolute ultimate game plan. Today, we are looking at what I like to call the championship final of mathematics exam strategy, graphs in practical situations. You know, when you walk into that exam hall, you've got maybe 90 minutes to glory, 90 minutes to prove everything you've learned. And graphs, well, they are usually the final boss. We're going to take all that complex data, the tricky curves, and those dense mathematical formulas straight from the syllabus, and we're going to break them all down into an absolute visual masterclass today. By the end of our time together, I promise you won't just be blindly memorizing formulas. No way. You are going to see exactly how to decode the hidden stories behind every single line, slope, and curve. You're going to walk into that exam feeling completely unstoppable.
But hey, before we get too comfortable, I want to pose a challenge directly to you right now. Think about this. Imagine an object whose speed is constantly changing. So on a graph, it's not a nice, neat, predictable straight line. It's a swooping curve. Here is the question. How do you calculate the exact speed of that object at one precise, frozen moment in time just by looking at a curved line? It sounds kind of like a trick question, doesn't it? I mean, how do you find a single speed when the speed is literally always changing? Well, I want you to keep this specific challenge in the back of your mind as we go, because resolving this exact question is the single most complex mathematical hurdle we are going to decode today, and it is worth a massive amount of marks.
Okay, let's dive into our progressive syllabus blueprint. This is our strategy for the day. First, we'll start with reading basic conversion graphs. Then, we move to mastering distance time graphs. From there, we are decoding speed time graphs and figuring out the area under them. Finally, we'll tackle those non-linear travel graphs. But before we continue to step 1, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Trust me, you do not want to miss the strategies we drop every single week. All right, let's get into it. Section 1. Reading basic conversion graphs. This is the foundation, guys. We're focusing on how basic straight lines help us effortlessly convert different real-world units.
Think of a straight line graph as a literal universal translator. It maps direct, proportional conversions perfectly. For example, our source material looks at an exchange rate where €1 equals exactly 8.80 South African Rand. Another classic exam example is 80 kilometers equaling 50 miles. To use this visual translator in the exam, you don't even need a calculator. You simply trace a point from your known value on the horizontal axis, move your finger straight up to the plotted line, and then trace straight across to the vertical axis. It's really that simple. So if you're looking at the horizontal axis for, say, 25 Rand, you literally just trace up to the line, then horizontally across to the left, and boom, you instantly see that drink costs roughly 2.80 euros. It is pure visual logic, and it's practically free marks if you just use a clear plastic ruler to guide your eyes. Always use a ruler, folks.
Now we transition to the next level of complexity. Section 2. Mastering distance time graphs. Here we are looking at how an object's distance changes over a continuous, ticking period of time.
Now, the absolute core concept we need to master here, and I mean really internalize, is the gradient. In mathematics, the gradient is just a fancy academic term for the slope or steepness of the line. But when you are looking at a distance time graph, that gradient represents something incredibly tangible. It represents speed. Why? Because the mathematical formula for speed is distance divided by time. So the visual steepness of that line on your paper directly equals the mathematical speed, usually measured in meters per second or kilometers per hour. So what does this actually mean for you? If you see a steeper line, the object is moving faster. It's covering more distance in less time. If you see a shallower, flatter line, it's moving slower. Just by glancing at the angles, you already know the story of how the object is moving.
Okay, everybody, listen up. Here is where we need to spot the trap. I literally cannot stress this enough because this right here is the absolute most common point of confusion that students face in exam scenarios. It costs thousands of students their top grades every year. Look at the comparison. On a distance time graph, a perfectly horizontal flat line means the distance is not changing as time ticks by, meaning the object is completely stationary. It's parked. It is not moving. But, and this is a massive but, if you look at a speed time graph, a horizontal line means the speed isn't changing. The object is still moving. It is just cruising along at a constant, steady speed. I've seen so many students lose marks because they just glance at a flat line and write the car stopped. Always, always, always check your vertical axis before you make any assumptions. Is it distance or is it speed?
That one check will save your grade.
Let's move deeper into the mechanics of motion with Section 3, Decoding Speed-Time Graphs. In this realm, that vertical axis now represents exactly how fast our object is traveling at any given second.
Let's break down the core rules for these graphs using a truly fantastic real-world example from our source material. Imagine a cheetah accelerating to chase down a gazelle. On a speed-time graph, a straight upward-sloping line means the cheetah is experiencing constant acceleration. It's getting faster and faster and faster. Then, when that line goes perfectly horizontal, it means the cheetah has hit its absolute top pace and is maintaining a constant, blistering speed across the savanna. Finally, a straight downward-sloping line means constant deceleration. The cheetah is exhausted and slowing down after the sprint. And just like we saw in the last section, the steepness, or the gradient of those lines, tells us the exact rate of that acceleration or deceleration. The steeper the line, the harder the cheetah is pushing.
Let's put some actual numbers to that gradient to see how it works in practice. Acceleration is simply the change in speed divided by the time it took to make that change. So imagine a car starting from a dead stop, 0 speed, and reaching 16 meters per second over a span of exactly 8 seconds. To find the acceleration, we take the total change in speed, which is 16, and we literally just divide it by the time, which is 8. 16 divided by 8. That gives us a precise, mathematically exact acceleration rate of 2 meters per second squared. And remember, the steeper that upward slope looks visually on your graph paper, the higher that final calculated number is going to be. It all connects back to the visual.
Section 4. The area under speed-time graphs. Now, prepare yourselves, because we are about to shift our focus to the ultimate hidden secret of these charts. But first, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to unlocking these hidden graph secrets.
So the absolutely crucial point you need to understand is this. Yes, the drawn line on a speed-time graph tells you all about acceleration and speed. We know that. But the blank, empty space sitting underneath that line, it holds a massive secret. The total area calculated completely under a speed-time graph gives you the total distance traveled by the object. Let that sink in. You don't need to memorize a complex, multivariable physics formula. By simply splitting that graph's empty area into really simple, basic geometric shapes that you learned years ago, like rectangles and triangles, we can calculate exactly how far an object moved. It's like a math magic trick, and examiners absolutely love testing this.
Okay, let's build this out together using some raw data right from the source. We're tracking a heavy train moving over a period of 30 seconds. Look at the table. For the first 10 seconds, at 0, 5, and 10, the speed stays exactly perfectly locked at 20 meters per second. It's cruising. Then, from 10 seconds all the way up to 30 seconds, the speed gradually and steadily increases from 20 up to 30 meters per second. Now think about what this looks like visually on the graph. This creates a big, flat rectangle for the first 10 seconds and then a trapezoid for the last 20 seconds. But working with a trapezoid can be clunky, right? So we just split that trapezoid horizontally into another rectangle with a nice, easy triangle sitting right on top of it.
And what happens when we calculate the area of those simple shapes? Let's do the math. The area of the first large rectangular block, the constant speed phase, is a width of 30 seconds times a height of 20 meters per second. Wait, scratch that. Let's look at the data again. The constant speed was only for the first 10 seconds. Actually, if you look at the total block across the whole 30 seconds, up to a height of 20, that's 30 times 20, which gives us an area of 600. Then we have the triangle sitting on top, representing the extra acceleration phase from 10 to 30 seconds. The base of that triangle is 20 seconds, the height goes from 20 up to 30, so the height is 10. The formula for a triangle is half base times height. Half of 20 is 10. 10 times 10 is 100. Add the rectangle 600 to the triangle's 100, and we reveal our total distance, exactly 700 meters. We just use basic primary school geometry to solve a dynamic, high-level physics and math problem. It is such an incredibly satisfying strategy when it finally clicks in your brain.
Awesome. Now this brings us to Section 5, Tackling Nonlinear Travel Graphs. This is the final, most advanced challenge of the entire explainer. Because in the real world, gradual motion doesn't always behave perfectly. It creates complex, sweeping curves instead of neat, predictable straight lines. Let's see how we conquer them.
Let's look at gravity. Our source material uses the classic example of a heavy stone dropped off a very tall cliff. The distance it falls isn't a straight, uniform line,
Because of gravity, it accelerates. It follows the formula distance equals 4.9 times time squared. As you can clearly see in the data table here, the distance is compounding exponentially. At 2 seconds, it's fallen 19.6 meters. By 10 seconds, it's plummeted 490 meters. When plotted on a graph paper, this produces a constantly changing, swooping upward curve. Now, remember the big challenge question I threw at you at the very beginning of this explainer? If the gradient, the steepness, is always constantly changing on a curve, how on earth do we calculate the exact speed at one specific frozen second?
Well, the answer is a magical thing called the tangent. A tangent is simply a straight line that you draw by eye using your ruler so that it grazes and touches the curve at one single solitary point. Nothing more, nothing less. And this brilliantly illustrates how we handle chaos and complexity in Cambridge mathematics. We cleverly turn a complex, curving, unpredictable problem into a highly solvable, simple straight line. Because the mathematical rule is this: the gradient of that straight tangent line is exactly the same as the gradient of the curve at that specific frozen moment in time. You literally build your own straight line to solve the curve.
Let's see exactly how this builds into an actionable 3-step strategy you can use to guarantee highly accurate readings in your next exam. Step 1. Take your clear plastic ruler and draw a straight tangent line grazing the outside of the curve at the exact time point the question asks for. Just let it kiss the edge of the curve. Step 2. Pick 2 clear, specific, easy-to-read points anywhere along your newly drawn straight tangent line. Pro tip here, pick points that are quite far apart from each other. It makes your math way more accurate. Step 3. Find the rise over the run. Divide the vertical height between those 2 points by the horizontal distance between them. That's it. You've just found the gradient of your tangent line, which means you have successfully calculated the precise speed of a nonlinear accelerating object at an exact frozen moment in time.
Look at how far we've come. We have covered everything today, from reading basic currency conversions to avoiding the stationary object traps to decoding the acceleration of a sprinting cheetah, all the way to drawing tangent lines to solve the mysteries of falling stones. You now possess the exact visual problem-solving skills required to read the stories hidden deep within the data. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So, here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at ACEXams_IGC to excel in your Cambridge examinations. Subscribe right now to @ACEXams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep practicing, stay sharp, and I'll see you in the next strategy session.